Hi guys. Okay, so our Unit 7 / Chapter 7 test is coming up next Thursday. So I wanted to film myself doing these review problems because I know we won't have time to do them in class. Just in case you're confused, I did attach the solutions, so the answers are on the back, but I wanted to make sure you knew how I got the answers and making sure you were doing it right and understood all of the different things that are on here, because I'll be testing you on each one of these different things. You'll probably have like 2 problems on each of these. So, sorry, my voice is kind of gone. Yeah, I'm just going to film myself doing a couple of these. So watch them, go through. If you have extra questions, email me, and make sure you study and are prepared for our test on Thursday so that you can get it right the first time. And you know it's just going to get harder, which is so exciting. But this is a really good introduction chapter, so I want to make sure you've really mastered and feel good about finding integrals in whatever situation. So the first one is slope fields, and you will be tested on slope fields and Euler's method. Not Euler's, Euler's. So go back through your notes from that day and make sure you remember how we did that Euler's method. That's when you have like some sort of curve and you're finding 2 points, and we use like the delta x and the slope rise over run to get to our next point and keep going from there. So review that, and then for number 1 for slope fields, really it's just kind of like looking at the problem and analyzing it and plugging stuff in. So like for this first one right here, I just looked at the picture and I saw as x was going to negative infinity, right, on the left side, then my slope was also going to negative infinity. It was getting really steep. And then same thing, as x went to positive infinity, it was going to positive infinity. So because of that, I looked at my first 2 and I was like, all right, well, if x is going to negative infinity, the negatives and the negatives would cancel out, and that wouldn't work. So a and b I canceled out. And then from this one, I just looked and plugged in different points. I was like, okay, let's pretend that x is 1 and y is 1, and let's see what's sort of happening. And yeah, I figured out the E was the most accurate one. So I guess that one's just sort of guess and check. Number 2, so that will be on your test, slope fields and Euler's method. So make sure you study that. Number 2 is U substitution. So this is, let's get some info going here. The integral of tangent x dx. We don't know what the integral of tangent is. Make sure you have that paper that we went over in class, the properties paper, and you memorize like what the integral of tangent squared, secant squared, those kind of things that we already know are for sure going to be easy. But tangent is not one that we like automatically know. So you switch it up. I'm going to write tangent as sine over cosine, right? Tangent's the same thing as sine over cosine, so you can totally write it like that. And this is good because now it's a division problem, which we can use U substitution for. So when I first was learning calculus, I was like, all right, we got this. I'm going to make U to be sine of x and du to be cosine x dx, because the derivative of sine is cosine. So I was like, oh, this works perfect because U is sine and du is cosine. So I'm like, this is amazing. Let's do this. So I write the integral of U over du. And I'm like, wow, nothing even has to change. This is so simple. Is it though? Does this work? The issue with this is that we can take the integral of U, that's no problem. But this du is telling us what we're taking our integral with respect to. So we're taking the integral with respect to U, but it's in the denominator. Like what? How do you take the integral of 1 over du? It doesn't really work. See what I'm saying? Usually we have our integrals of some function, and then our du, our dx, we'll just say this is x squared plus x, is on the outside like that. So if it's in the denominator, it doesn't work. That's not going to happen for us. So as simple as this looks, it's not going to pan out. So let's try again. No problem. If you guess wrong, it's like whatever. Just try it again. Pick something else. So this time, instead of making my U sine, I'm going to make my U cosine of x. And now, if I derivative that, the derivative of cosine x is negative sine x dx. So this doesn't work out quite as well. U is cosine, so that's easy, but du is negative sine x, and we have a positive sine x. As long as it's a constant, it's not that big of a deal if it doesn't match. Just compensate for the constant by adding another constant. So I'm going to put a -1 out front. if I times by -1, then I can times the inside also by -1. So negative sine x over cosine x dx. And now it matches. Yes? So, sorry, my computer just turned off. I want to make sure you're still filming. All right, so now it matches, so now you just plug it in. So I leave that -1 out front, the integral. Negative sine x dx is the same thing as du, so that's on top now, which is what we want. And then u cosine x is in my denominator. So I could also rewrite this as the integral of 1 over u du, which sort of is a little bit clearer. Can you integrate 1 over u? What's the integral of 1 over u? Hopefully a light bulb was going off, like obviously. This is the same every time. The integral of 1 over u is going to be ln of u. And then it's negative, so throw a negative in front, and then because we're integrating, there should be a plus c on the end. So that's fun and exciting. Sorry, I'm like kind of all over the place. We're almost done. Finally, got to plug that u back in once you're done. So I'm going to do negative ln, and then u was cosine x, and then plus c. So if you look on number 2, it's d. Cool? Easy, hopefully. All right, that was u substitution. So you will definitely have some u substitutions questions on your test. So make sure you're clear, feeling good about how to do u substitution, how to pick your u, how to find du and plug it in, and all that good stuff. Number 3 is an example of integration by parts. That's the 3rd standard on your test. This is the ultraviolet voodoo one. You'll have to do this for sure. So number 3 is the integral of x times e to the 2x dx. So this one's a product rule. Often with product rules, it's either u substitution like chain rule, but in this case, the integral, or when you take the derivative of e to the 2x, the integral, or the derivative of 2x is just 2, not x. So you can tell that this isn't u substitution. This one's going to be integration by parts. So let's do it. Integration by parts is when you pick u and dv to begin. And then from there, we'll find du and we'll find v. So if you remember how to pick your u, we have our fabulous little acronym LIATE. L is logarithms, there's no logarithms. I is inverse trig, no inverse trig. A is algebra. There is some algebra. Algebra is just like x's, x squareds, polynomials type situation. So my u is going to be x. So if this little piece is u, then dv has to be the rest of this. So dv will be e to the 2x dx. Has to take up the whole thing. All right, if u is x, then du is 1. We really like that. When you're doing integration by parts, you want your du, because, okay, the formula is ultraviolet minus integral of v du. So what you're going to have to do is you're going to have to integrate v du. So you want either your v or your du to be something that's really simple. Usually your v isn't because it's an integral, but oftentimes you can get your du to sort of disappear, like we did right here. So this is a good sign. You probably picked the right u if your du is 1 or something easy, right? All right, and then v is the integral of this. The integral of e to the 2x is e to the 2x. We got to compensate for taking the derivative of 2x, which is 2, so I'm going to throw a 1/2 in front of there. Remember that? See how I did that? Great. So then you just plug it into the equation. So uv, u is x, v is 1/2 e to the 2x, minus the integral of v, 1/2 e to the 2x, du, which is just 1. Oh, technically the integral of x was 1 dx, so we can put that on there. And that's where our dx comes in. Fabulous. So now this is much easier to integrate than it originally was. So blessed. This thing becomes x e to the 2x over 2. I'm just sort of simplifying that. Minus the integral of 1/2 e to the 2x is e to the 2x over 4. See how I got that? If you integrate, or if you take the derivative of this, you keep e to the 2x, but then the derivative of 2x is just 2, so you bring a 2 out front. So I needed my 2/4 to simplify to 1/2, so that I have the 1/2. And then obviously there's a plus c on the end. So x e to the 2x over 2 minus e to the 2x over 4 plus c is a. So number 3 is a. So that's an integration by parts example. Cool, hopefully. You'll have a couple of those on your test. Okay, number 4, if you flip it over, number 4 is from section 7.4. This is our exponential equations section. So let's talk about this one. This one looks scary. It actually has quite a few steps, but they're good practice. So it tells you the rate at which acreage is being consumed. So the rate, dA dt, is being consumed by a plot of I don't know what that word is proportional to the number of acres already consumed at time t. So is proportional to the number of acres. That's what it's telling you. The rate is proportional to the initial number of acres. You've seen this, hopefully, before. We talked about this in class. And if you remember, if you separate the variables on this, you multiply both sides by dt. And then you need the a to come over here. So you end up with dA over a equals k dt. And then you just integrate that to get rid of the dA and the dt. So the integral of 1 over a is ln of a, and the integral of k is just kt. And then to get rid of this, we just take the e of both sides. So we're left with a equals e to the kt plus c. Adding variables lets you multiply. So plus c is the same thing as timesing by e to the c. So this is where we end up with this equation where we have y equals y naught e to the kt. Where our y naught, our initial condition, is just this constant, this e to the c. Yes, so we remember this? So whenever it tells you the rate that is proportional to the number of acres, you know automatically that we're using this exponential equation right here. Yeah, so that was the tell. So read that really carefully. This is the equation we're using. It's an exponential increasing equation. And then it gives us some info. It tells us that there are 2 acres consumed when t equals 1. So let's write this down. When t equals 1, there are 2 acres consumed. And then when t equals 5, there are 3 acres consumed. And it wants to know when t equals 8, how many acres will be consumed. So they kind of give us a lot of information, which is fabulous, but we're going to have to do a little bit of solving and math. All right, let's do it. So we're going to start with this first thing that they gave us right here. So it told us when t equals 1, my answer was 2. So my answer is 2 when t, we don't know what k is yet, when t is 1. Cool. And then it told us my answer is 3, my acreage is 3, when t is 5. So k times 5. Yeah? These are 2 equations. And we don't know our y naught, we don't know how much we're starting with, and we don't know our k. So if we have 2 equations and 2 unknowns, can we solve for those? Yes, we can. So what I did is I solved for y naught in both of them. So if you solve for y naught, you just divide both sides by e. So I get 2 over e to the k. K times 1 is just k. And then if I solve for y naught here, I divide both sides by e to the k-fifth. So I get 3 over e to the 5k. So I solve for y naught in both of those. If both of these things equal y naught, then I can set them equal to each other. So I did 2 over e to the k equals 3 over e to the 5k, which is valid because in this situation our y naught should be the same. And then from here I just solved, so I cross multiplied. So 2 to the e to the 5k equals 3 times e to the k. Divide by 3. No, I want to do that differently. I'm going to divide by e to the k over here. And I divide by 2 on this side. So e to the 5k over e to the k, if you remember, when we divide numbers that have an exponent, it turns into subtraction. So this is e to the 5k minus 1k. 5 minus 1 is 4. So e to the 4k is what I get. And then over here, 3 divided by 2 is 1.5. Hopefully you can solve this. Remember, we're trying to figure out what k is. So what I do is I take the ln of both sides. ln and e cancel, so I'm left with 4k equals the ln of 1.5. Divide by 4, and this is your k. So I typed that into my calculator, and my k ended up being k equals 0.101366. Yay! So I found the k. That was so exciting. Now that I have that, we're almost ready. The last thing you need is just this y naught. So you can just take the k and plug it into either of these equations and figure out what your y naught is. I think it's like 2.23 or something. I don't know where my work is, but I solved for it somewhere. So just plug it back in and solve for k, or solve for y naught, so you know what your two things are. And then finally, you can get your final answer. You'll just say, what is my answer? Y equals what? When y naught, again, sorry, I don't know where it is. I think it was, oh, maybe it wasn't 2.3. That was a different problem. Man, I'll just do it. One sec. Let me grab my calculator. All right. So hopefully you have a calculator with you. Just plug it in. So 2 divided by e to the k, 0.101366, is 1.8072. 1.8072. We still have e. Our k is this, 0.101366, and our time is 8. So if I take this and I times it by e to the 0.101366 times 8, I get 4.0662, which is C, 4.066. So 4.066. Yay, I did it. So honestly, the most important part of this is reading it and knowing that I'm talking about this separable differential equation, the dA dt equals k times a. If you know that we have this proportional relationship with the rate, then you know you're using this exponential equation. And then the rest of this is just algebra. So remember, do the full thing, work it all out, make sure you remember how to solve for two equations, two unknowns, you know, plugging stuff in, make sure you know how to work with e and natural logarithms, right? Make sure you remember that division, like 8 to the 5th divided by 8 to the 2nd is 8 to the 3rd. You just subtract. And it works the same way for multiplication and addition. So make sure you remember this stuff because it helps you when it comes to solving. Yeah, so it looks kind of long, but it's just a lot of algebra. Holler if that was confusing or you have questions on that. Okay, this is the last one I'm going to do in this video. Where are we at? 17 minutes. Yikes, I'm so long-winded. I apologize. Okay, let's do number 5. So, number 5... Actually, it was a little mean of me to put on there because you can't actually solve it by hand. But I want to talk about the calculator, so it'll be good. So what it tells you is, it says, let f of x be an antiderivative. So f of x is the antiderivative of cosine of x squared. So that means f of x equals the integral of cosine of x squared dx. Cool. So I first looked at this and I'm like, great, we'll just integrate it. So I'm like, maybe I use integration by parts. So I'm like, okay, if u is cosine x squared, then du is going to be 2x. There's not a 2x in here. That doesn't make it easier. What? Not working. So yeah, substitution isn't working. Integration by parts isn't working. This looks so simple, but it actually isn't something you can do by hand. There's a couple different methods, but I didn't go over them in class. You don't need to learn it. So off the top of your head, you're not being able to integrate this. You're like, I can't even find the integral. So how am I going to figure out what f of x is? Well, let's use what they tell us. So it tells us, this is from last chapter. We know that the integral from a to x of cosine of t squared dt is just cosine of x squared, right, if we derivative that. So what we do is we use these initial conditions, f of 1 equals 0. So if I plug in 1 for x, this whole thing equals 0. So what does a have to be? If I'm integrating from a to 1 and I want this whole thing to be 0, what is a? Hopefully you're answering the screen right now that the answer is 1. Right? Because the integral from 1 to 1 is obviously going to be 0. If you integrate over no space, the area under the curve will be nothing. So we figure out that a is 1, and then it wants to know what happens when f is 5, or f of 5, which means x is 5. So really it's just asking the integral from 1 to 5. So it starts off looking tricky, looking like an integral problem, but really it's asking you if you can figure out that I'm integrating from 1 to 5. So from here, I just typed it straight in my calculator. Definite integrals your calculator can do. So the integral from 1 to 5 of cosine t squared dt. So I'll show you real quick. You might have to do this on the AP test. I don't know. So check this out. Okay, let me get back to the main screen. So I press exit all the way till I'm back to the main screen. Hopefully this is showing up correctly for y'all. Okay, so I want to take an integral. So I'm going to go to options, and then you see there's a little, this says calc. That stands for calculus. So click on that. And then it has a bunch of different options, derivatives, second derivatives, this little, see that little integral dx? So I'm going to click this button. Great, now it's asking me to take the integral. Yay. So I'm taking the integral of cosine x squared. So I got to do cosine, and then I'm going to do it of x squared. I'm literally just looking in the, oh, here's the squared, in the computer, so this is really hard. All right, cosine x squared. Throw the comma in there, so that's the function we're integrating over, and then you got to tell it we're going from 1, so I go 1, comma, to 5. And then I'll close the parentheses. So I'm asking it to take the integral of cosine x squared from 1 to 5. And your calculator's just approximating this like we did last unit with rectangles. Takes a second. And there it did it. Negative 0.293057. Check that out. It's C, negative 0.293. Cool, right? If you have the Inspire like this, you will just press Control and then this button right here, and it brings up, hang on team. Okay, seriously? Don't press Control, just press the button. And it brings up this option, and it lets you like actually calculate the integral. So you just type it in from 1 to 5 of cosine squared, and it does the same thing. 1 to 5 of cosine x squared dx, and then it does it for you and gives you the answer. Cool? So that's how I finished that one. Set it up, make sure you know how to integrate a definite integral still. Make sure you recall how this works out. And if it's something totally crazy, use your calculator. I lied. I thought that was going to be the last one, but I want to do 6, and then I'll do 7 in a different video because that one's a little bit longer. 6 is not too bad. Okay, so number 6 is about partial fractions. And I spent a decent amount of class time going over how to work with partial fractions, so I really like this problem. This is good practice. You'll have one like this on your test. So number 6 asks you to find the integral of dx over x minus 1 and x plus 3. And this one's really nice and easy because you can tell clearly that this is a function, a polynomial over a polynomial, and these ones are really easy to split apart. They're already factored for you, and they're at degree 1. Each of these are degree 1, which makes your life much easier. So if I want to figure out how to integrate this, I can't do it from here, but I could do it if I could split it into 2 separate fractions. So this is where I do a over x minus 1 plus b over x plus 3 equals, there's nothing on top, it's just a 1 over x minus 1 times x plus 3. So what I'm doing is I'm taking this combined fraction and I'm splitting it apart so that I can integrate each of these pieces. Because when they're in pieces, they're so much easier to integrate. So if you remember, if I want to add this up, I have to times a by this one, x plus 3. And then I've got to times b by this one, x minus 1. And this whole thing has to equal 1 as my numerator. So I'm just going to solve. I'm going to set x equal to negative 3. Pretend that x is negative 3. So then this goes away, which is really nice. If x is negative 3, then this says negative 4b equals 1. And if I solve that, I get that b equals 1 over negative 4, or negative 1/4 for b. Now I did the same thing. I'm going to pretend that x equals positive 1 so that the b goes away. If x is positive 1, I'm left with 4a equals 1. So I get that a equals positive 1/4. Cool. So I solve for both of those, then I can plug them back into my fraction. So a is 1/4, so I'm going to put 1/4 on top, and then divided by x minus 1. And then plus b is negative 1/4 divided by x plus 3. So now I'm taking the integral of this whole thing, which I guess looks a little scary, but it actually is easier. So the integral, if I have a little constant like 1/4, I'm just going to leave this chilling out front, 1/4. And then the integral of 1 over x minus 1, 1 over whenever x is in your denominator, it's ln, the natural log of x minus 1. And this one's really easy because the derivative of the inside, the derivative of x, is just 1. So we don't need any weird constant stuff happening. It's just that function. And then this one is negative, so I'm going to put minus 1/4. And the derivative of 1 over x plus 3 is ln of x plus 3 plus c. Cool? Sorry, that's really low. I hope you can see it. So that was my integral. And then the last thing is just you got to use integral properties to simplify this. So when you have two logarithms or natural logs and they're being subtracted from one another, subtraction turns into division. Yes, we've been going over this. So I'm going to keep the 1/4 out front. And I'm going to keep the ln. And then the x minus 1 goes on top. And the x plus 3 goes on bottom. And then there's a plus c on the outside. As usual, natural logs get tricky with negatives, so a lot of times we'll call this an absolute value. So let's be precise and make it look like that. And that's the answer that I put on your solutions guide. So that's how we got there. Cool. Practice splitting using partial fractions. That will be on your test too. Okay, that's going to conclude my first video. I'm going to do number 7, the kind of like word problem with you. I'm going to show you the whole proof of it because we didn't have time in class. So I'm going to do a separate video for that. So hopefully you made it all the way through this. Congratulations. Hopefully that helped. Email me, text me if you have questions, and rewatch parts that were confusing. And watch the next video on number 7, please, because it's going to be important.